Teleportation will commence in 5 minutes. Do not leave any luggage unattended. Unattended luggage will be removed and destroyed. Attention, ladies and gentlemen. This is an announcement from planet X31. Please take your seats. Teleportation will commence in 2 minutes.
Earthlings, this is your host speaking. Science in Cocktails is an initiative taken by the Niels Bohr Institute together with Boons News, such that science and scientific research can reach all of you Earthlings. Science only reaches people through the media and in often cases distorted. Science in Cocktails provides a unique experience where everyone can interact with the scientist in person. Tonight's teleportation will be guided by Jens Gaardhøje, professor at the Niels Bohr Institute and nuclear physicist. He will take you through the realm of nuclear energy, nuclear power, nuclear reactors. He will explain the processes of nuclear fission, of nuclear fusion. He will digress over the issues and challenges of creating sustainable nuclear energy and harmless for society. Nuclear energy will be transformed in creative energy, and this process will be represented by the artist Henrik Schutz. End of transmission.
Okay, let's give an applause to Professor Jens Gaardhøje.
Okay, good evening, everybody. I'm pleased to see so many of you here on the 1st of May, where the sun has been shining outside and many other good things to do. So, yeah, well, I've been asked to talk about nuclear energy, and so I found this old cartoon by Bohr. I think this is from 1979. And, well, it's a train that pulls into the station, and the train driver, he's suddenly looking back to what's left of his train. And then he said, well, it all started around Svanemøllen station with a discussion about the peaceful use of atomic energy, right? So, so this was very much up in the public debate in the late 70s and also the 80s, and somehow the discussion has abated a bit. Now it has new fuel, so to speak, after the Fukushima incident. And I'm not going to discuss the politics of energy production, nuclear energy production, but I think it's a good idea when one engages in the debate to actually know what the physical fundaments are and what are the basic principles. So that's what I hope I will be able to entertain you with this evening. So it's nuclear fusion and nuclear fission on Earth and in the stars. And this is a picture of our sun, which produces energy by fusion processes deep into its interior. And then the energy is released and reaches the Earth as radiation, as light. And we get about, in Denmark, I think we get 500 watts per square meter from the sun. But what is actually happening inside? This is an overview of our world as we physicists see it on different scales. So here at the largest scale is our own one, the matter that surrounds us. But if we look at it a little bit more closely and we go down to the scale of typically a micrometer, millions of a meter, then we see that the matter is composed of atoms, and these atoms can sometimes be arranged in regular patterns, that is what we call crystals. If we zoom in a bit more on the atom, we see that the atom is a complex object that has a nucleus and is surrounded by electrons. And all of chemistry and everything in daily life is essentially governed by the electrons. So chemical reactions are governed by how electrons are shared between different atoms and creating molecules. So life, chemistry, and biology is all at the level of the atom. But if we zoom in a bit more, then we have the nucleus, which here's also a length scale. So we're going from the atom, we have to go about 5 orders of magnitude. That's about a factor of 100,000 smaller. Then we have the nucleus. So this picture here is, of course, completely off scale. if the atom was about this big here, then the nucleus would essentially be a pinpoint somewhere, I don't know, around Roskilde or something like that. Okay? So, and all the mass of the atom is concentrated in the nucleus. The nucleus consists of two types of particles, protons, which have a positive electrical charge, and neutrons. And it's rather dense conglomerate. So again, if we were to blow up a nucleus to the size of a golf ball, the mass would be that of a supertanker. So the nucleus is extremely dense, and in a sense, it's the mass in the universe is carried by nuclei. Then the protons and neutrons again have a substructure. We know today that they consist of quarks, and they are bound by particles called gluons. And in fact, my own research deals with these deeper layers, but today we'll concentrate on the level of the nucleus. Now, I've also written up here an energy scale. And it is so that every time you try to probe a deeper layer, you have to increase the energy, because the system, this is a consequence of quantum mechanics, that if you have to put a particle or confine it in small dimensions, because essentially of the uncertainty relation, then you have to have a very high energy to keep it inside this small spot. So if you want to keep a particle inside the volume of an atomic nucleus, then you have to have very high energies. And these energies are typically millions or billions of times higher than the energies that we are dealing with when we are doing chemistry or we are doing biology in our everyday world. This also, of course, has the potential that transformations at the level of an atomic nucleus can also release a lot of energy. And that's, of course, where the potential or the interest in energy production from nuclear physics arises. This is a picture of all the isotopes that we have in nature, the nuclei that we have in nature. So down here we have an axis that goes this way. This is the number of neutrons that are inside a nucleus. Here is a picture of it. And here is the number of protons. Now the stable nuclei in nature, those that live for billions of years, for an age, for a time that is comparable to the age of the Earth or the age of the universe, are the ones that are in black here. And down here we have hydrogen, and we have carbon and oxygen, and the very familiar elements in nature. And as we go higher and higher, we can see that this curve bends a little bit. And you can also see that the black points, as some up here in the upper edge of the diagram, they stop. So the stable elements, the heaviest of the stable elements that we have in nature is actually uranium. And there's a reason for that, and that is that as nuclei contain positive charges, the protons, then as you make a system bigger and bigger, you put more and more neutrons and protons in there, then the electrical forces are going to be repulsive, and eventually they will pull the nucleus apart. So there must be a limit in the upper edge, and the upper edge is actually at uranium. Now, we can, with human ingenuity, we can realize the old dream of the alchemist. We can actually make new nuclei, and we can also make nuclei that are beyond the boundary of uranium. And we can do that by using accelerators and colliding nuclei, and you can sometimes make them stick together. But basically, this is what we have to do within nature. So we have the black points are the stable ones, and the envelopes here in gray show all the nuclei that in principle can be made. Because at some point, if you try to stick on another particle, it will no longer be bound, and this sort of outlines the possibility or the space you have of different nuclei. So there's about 4,500 nuclei here. But pay attention here to the end, and to particularly the fact uranium, because I'll come back to that. So we have to know something about atomic nuclei, and the first thing we can do is we can try to measure their masses. And I won't go into details, but you can use a spectrometer, with the process known as mass spectrometry, so that if you have atoms of a given kind, which contain nuclei that you want to study, you may be able to take away an electron, therefore the atom becomes electrically charged, and then you can, with a voltage, you could actually pull at it. And then you can send it through an electrical field and a magnetic spectrograph, and then you can actually separate, if you have different isotopes of a given species, for example, uranium, then the meaning of the word isotopes is that you have the same number of protons, but you have different number of neutrons. The neutrons have no charge, so they in a sense just contribute to the mass. But then, if you send a beam of uranium nuclei to such a mass spectrometer, the heavy ones in a given magnetic field, the heavy ones will be deflected a little less than the lighter ones. And in principle, if the device is big enough, you can actually separate the different isotopes of a given chemical element. If you know all the details of the instrumentation here, you can also determine with actually very high precision the mass of these different atomic nuclei, or the atoms, which also include the electrons. And that's a long story, but what one finds when one measures the masses is actually that the mass of the combined system is lower than the mass or the energy of the combined system is lower than the energy or the mass of the pieces. And I can maybe show you here in a more pictorial way. So you have a scale, you have an assembly of neutrons and protons, shown here. And over here on the other side of the scale, we have the individual constituents, the neutrons and protons disassembled. And it turns out that these actually weigh more than the combined system. And that is the secret of nuclear energy. Because there's a mass difference here, and Einstein told us in 1905 the famous formula E equal to mc squared. So there's an equivalence between energy and mass. So the missing mass here corresponds to an energy. And this energy is the energy that actually binds all these pieces together to make the nucleus. So obviously we can go the other way around. We can take a nucleus and we can chop it in two, and then this is at least going part of the way to disassembling it completely, and therefore we can convert the mass difference into energy. And that is the basic principle of nuclear energy. Okay? Okay, so people have had a great fun over many years in trying to measure the masses of different nuclei to a very high degree of precision. And typically you have to go to many decimals because the energy that is to be calculated from the mass differences is actually a small component or a small part of the total mass of a nucleus or a nuclear particle. So people have tabulated all this, and my intention is not that you should read all of this or learn it by heart, but here are different elements, and this table actually continues for many pages. But these numbers are available, and they are well measured, and they can be used for calculational purposes. Now, when you have such a table, then you can begin to plot some systematic features, and that is what I try to show here. So this is the binding energy. Now, if you have all these masses, you take a nucleus, and then you have measured this mass. You know how many neutrons and protons it's composed of. Then you can calculate the mass difference between the composite system and the sum of the pieces, okay? And by Einstein's famous formula, E equal to mc squared, you could convert that mass difference to an energy. Now you can plot that binding energy, as it's called, this energy difference, divided by the number of particles that were in the nucleus. And this is what I plot here. It's called B divided by A, and it's the binding energy per nucleon. Nucleon is a common term for neutrons and protons. And this is a very famous curve, because what it shows is that if you take this binding energy for every nucleus that we know, divide by how many particles are inside, and plot it as a function of the number of neutrons and protons in the nuclei, then you actually get a very regular curve. Now, the curve is not flat. As you can see, it has a peak. And it has a peak here with an element that I have highlighted, it's iron 56. Now, the peak in the curve corresponds to the situation where you have the most binding energy per particle inside the nucleus. So obviously, the peak is where you have the most stable nucleus. So iron 56 is the most stable nucleus in nature. This is also why people have conjectured that if we wait long enough, the whole universe, if it continues to expand, it will cool, and eventually all matter would end up in the most stable configuration would be iron 56. So the universe would end up as a piece of iron, so to speak. Very dilute, but a piece of iron. Okay? So this comes just from the fact that iron 56 is the most stable of them all. Now you can also see that the curve drops off here towards the lighter nuclei. Down here we have the simplest nucleus, which consists of one proton and one neutron. That's called deuterium. And you have up here helium-4 is the next one, 2 protons, 2 neutrons. You have lithium, 3 protons, 3 neutrons, and so forth. And the curve crawls up. And if you go on the other side, you also see that the curve drops off. And up here at the end, you have, for example, uranium, in this particular case, uranium-238. Now, what does it mean that the curve has a maximum and drops off to both sides? Well, it says, again, this is the most stable element, but that also means that if you could combine some of the lighter pieces, then you would make a system that is heavier, and that would lie higher up on this curve. So it would be more bound. So by doing this process of merging two things, two light atomic nuclei, making a fusion out of these two, you can liberate energy. On the other hand, if you go over the right-hand side, you take a big one, like this uranium here, with 238 constituents inside, and suppose you chop it up in two, then you will make two lighter pieces which have masses around 90, so it's around here. And you can see that they lie higher up on the curve. So it's the same phenomenon that by splitting a big system, you actually produce two pieces which are tighter bound, which are more stable. And the energy difference is one that you can free. And that is basically the idea of fission, which is on this side of the diagram, and fusion, which is on this side of the diagram. Now, we actually have a very good explanation for why the curve has this shape, and that is because we can actually think of an atomic nucleus in many ways as a little drop of liquid. And inside the drop, the individual particles, they interact. So there's an attractive force, which is called the strong nuclear force. And you also have a repulsive force. And in a drop, you also know that if the drop is small, then you have a the surface of the drop has a large importance. And if you are at the surface, then you're less bound, because if you are at the surface, you only have neighbors on the inside, you have no neighbors on the outside. But if you have a big system, then on average, you have neighbors on all sides. So this explains why the curve drops off here, and also why it drops off here. And one can explain this or parameterize it mathematically, but that's not so important. The important thing is really the shape of this curve, because that is the reason behind all energy releases coming from nuclear reactions. So if we are in the high end, then we saw before that if we can split or make fission of a heavy nucleus, we can release energy. And the way the process typically is depicted is this one. Suppose you have a uranium nucleus, and somehow you can trigger it to become unstable. For example, by bombarding it with a neutron, then the uranium nucleus will begin to vibrate, and then at some point it may acquire an elongated shape, like is shown here. And if this continues, then it will develop a neck, and then it will break into two pieces, like here. And then sometimes, or on the average, there's a number of neutral particles, neutrons, that are also released. And already in this diagram, you can see the concept of the chain reaction. And that is that if by some means you are able to utilize these neutrons to bombard other uranium nuclei, then obviously you could have a chain reaction, because every fission of one uranium nucleus could in principle, if all the conditions are right, could in principle trigger another 3. And since the processes occur in a very short time, we are typically talking about 10 to the minus 15 or 10 to the minus 18 seconds, then if you have a dense enough system and every neutron trigger a new one, you would have a chain reaction that runs wild or proceeds in less than a billionth of a second. Okay? So this is basically the idea. And the energy release comes from the binding energy. And what happens to this binding energy? I mean, how does it come out? How does it materialize? Well, these two chunks here, which typically are half a uranium nucleus, they contain the red particles here, which were the protons. They are electrically charged. So you have these two nuclei that initially have just been separated. They have big electrical charges. They're close to each other, and of course they will repel each other. So they will move away with a high velocity, and eventually these nuclei are going to be stopped somewhere. And when they are stopped, the kinetic energy, the motional energy that they have, is going to be transformed into heat. And the heat is then something you can use to drive a turbine and produce electricity. So this is the basic idea of fission. So when do things fission? Well, I've attempted to describe the situation. So up here you have an energy axis, and here you have what you could think of as the separation of the two pieces that eventually will come out of a fission. Okay? And you can see here that there's kind of there's a barrier. It's like you're up in a mountain, and then you have a plateau on the mountain. But to get away from this plateau, then you have to climb over a hill in order to get down into the more general valley and down to the rest of civilization. And since with fission, it's the same thing, that you can live for a long time up in this little plateau here behind the hill. But if you are supplied with enough energy, then you can jump over this barrier. And that is precisely what happens with the uranium nuclei. Uranium-235 and uranium-238. Uranium-2 have very long lifetimes. So normally they are actually rather stable. Uranium-238 is in excess of several billion years, and uranium-235 has a half-life of around 700 million years. So in many ways, we would consider this as rather stable objects. But now we can induce the fission. We can make the fission happen. And in order to do that, we have to transfer sufficient energy to the uranium nucleus, which is lying up here with its own energy in this little valley, to climb over this barrier. And that we could do, for example, by shooting a neutron into it. That will deposit some energy inside the uranium nucleus, and that could be enough for it to climb over the fission barrier and then move away in this direction here, so that the two halves, so to speak, move away from each other. Okay? So this is called this barrier is called the fission barrier, and the amount of energy that you need to climb over the fission barrier is called the activation energy. Okay? So this height here is called the activation energy, and one can then plot the activation energy, how much energy is needed to induce fission for different elements. We start down with the light ones and the heavy ones, and you can see there's a curve in some particular energy units, and here around nuclei with mass 100, this activation energy is very high, but as we go over to the very heavy nuclei, the activation energy is extremely small. And the very heavy nuclei are those at the end of this table of the isotopes that I showed you initially. So it's, for example, it's around uranium and some of the neighbors of uranium. So this is why one uses the heavy elements, because they have a low fission barrier and require a low activation energy. Then they also release a lot of energy, because the gain in energy from being out at the end of the curve up to the top of this binding energy curve is the biggest possible. Okay, of course, nuclei can also can also fission spontaneously. We don't have to induce them. And that's why in nature, we have radioactive elements. It means that, in the previous plot, that either we get over the barrier, but that's the way we would think about it in classical physics. But we also know that quantum mechanics introduces some other things. Quantum mechanics tells us that in order to get out of a trap, we don't necessarily have to climb over the top of the trap, but we can also actually move through the barrier, we can move through the walls. And this is something that one cannot understand in classical physics, but quantum mechanics allows us actually to calculate, and we have verified it so many times, that you can actually move through the barrier. And that is this is the reason why, for example, the uraniums have such a very long half-life. We were talking about billions of years. And that is that they don't have energy enough to climb over the barrier. There is a barrier, there is a wall, but there is a finite probability that you can actually move through the barrier. And this is called barrier tunneling, barrier penetration or tunneling effects. Okay? So the spontaneous fission of elements in nature is due to tunneling through this fission barrier, and it is a quantum mechanical effect. Now, if something fissions, then it breaks in two pieces, and this is the measured distribution of the two pieces. So here you have the mass number. So imagine that we start, for example, with uranium, which has about 235 or 238 pieces. Then typically, when a fission fragment, in fact, this plot here is for uranium-235, then it's the masses of the pieces that come out. Okay, and you can see that there's a big peak here, and there's sort of around mass 95 or so. And over here, there's a peak at around 140. And 140 plus 95 is 235, so everything's okay. So every time you have one fragment that has a mass here, well, the difference up to 235 is on the other side, okay? And these are then the remnants of a fission of uranium-235, okay? And I have listed here some of the pieces, and they are the ones that we are worried about and we discuss when we talk about radioactive waste from a nuclear reactor, a fission reactor, because when the fission happens and the uranium nuclei split in two, then you end up with pieces like this. And here are some examples, namely strontium-90 on this side, and over here you have, for example, cesium-137 and iodine-131 and 129. They can have quite different half-lives, but they are typically relatively short. The strontium here has a half-life. A half-life means that you have 1 kilogram today, then in this particular instance, in 29 years later, then you will have only half a kilogram, and another 29 years later will be down to a quarter, okay? That's what half-life means. So, so these fragments from the uranium process are radioactive, and some of them have these half-lives. Now, the reason I have picked those out is, of course, that they are important for us humans, because strontium chemically behaves a lot like calcium. Calcium is something we have in our bones. So strontium binds, for example, this strontium-90 that can come out of a fission process, binds in the body like calcium. And you don't want to have a little radioactive source sitting in your bones very close to the place where you actually produce red blood cells. You have other things. You have iodine. Iodine has a tendency to concentrate in the thyroid glands, and so forth. And there are quite a number of the fission fragments, of the pieces that come out of uranium fission that are radioactive, and some of them have chemical properties that make them particularly unpleasant for humans. Okay? So this is really the radioactive fission waste that we are also very concerned about, and I'll come back to that in a moment. Okay? Now here comes a rather complicated plot. There are only 2 plots of this, but I think I wanted to include them because the question is always, what is this whole story about uranium? Why 235 and not 238 uranium? Okay? Now, what is plotted here is the probability for either a uranium-235 nucleus or a 238 nucleus to absorb a neutron. You remember, to induce a fission, the first thing you have to do is you have to absorb a neutron. Okay? And this is plotted in this diagram here, and it's a curve, but it's a little difficult to see. I will add some other colors in a moment. So I have highlighted some of the major trends here in red. So there's a curve. This is a logarithmic scale, so it actually drops a lot. So this is the probability for absorbing a neutron as a function of the energy of the neutron. Okay? Down here is what we call the thermal region. So these are neutrons that move essentially at a few kilometers per second. And over here we have 1, then we have 1,000, then we have 1,000,000 units, which are electron volts, so it's an energy unit. So these over here are fast neutrons, and these are slow neutrons. Okay? So in uranium-235, the probability for absorbing a neutron is very much higher at low energies. In uranium-238, we have a similar curve, but you also note that there's the scale here. I've tried to highlight it with the yellow band so you can compare the left side and the right-hand side. You can see that the probability of absorbing a nucleus in uranium-238 is much smaller. It's at least 2 orders of magnitude lower in uranium-238. Okay? So that's one part of the story. But now here I've also plotted what is the probability that if you absorb a neutron, that you fission, because now we are talking about the efficiency of the fission process, okay? So this is what I've tried to draw here in green, and at a first glance you can see there's a big difference between the left-hand side and the right-hand side. The left-hand side, the fission probability runs here, the green curve, and on the right-hand side, there's no fission probability until you come to the very high energies here of neutrons, and then suddenly the fission probability is coming up. But there's a difference in level between here and there of at least 3 orders of magnitude, at least a factor of 1,000, or between 1,000 and 10,000. So what is the message from all of this? The message is that in uranium-235, you have a quite high fission probability. You also have a high probability for capturing a neutron, but in essentially 10 times, well, the ratio of the probabilities for fission to capture is about a factor of 10. So fission is quite probable. On the other hand, in uranium-238, the fission probability is extremely small and requires very high neutrons. Now, when a uranium nucleus breaks into 2 pieces in one of the previous plots, I show you got 2 chunks out of it, but you also on the average got 2 to 3 new neutrons. And these neutrons that come out typically have energies in this domain here. So they have energy that is rarely high enough to actually induce the fission. And that would mean that if you have uranium-235, then the neutrons that come out will not initiate a fission in another uranium-230, or a fission of a 238, and you get 3 neutrons, then these neutrons will not initiate a fission in another 238. But if you're in your reactor, or you have a high concentration of uranium-235, then you can see that the 3 neutrons, if in particular you're able to slow them down so that from this energy they move down to this energy, then the fission probability is extremely high. Okay? So this is really the basic principle of constructing a reactor, and that is that you want to use uranium-235, you want to use neutrons of low energy, therefore you have to have a medium that is able to make the produced neutrons lose energy, and you can do that like you do when you play billiards, right? Then you have, when you shoot one billiard ball against another billiard ball, then, well, if you hit it absolutely head on, then your cue ball will transfer all of its energy to the other one. If you hit it completely at a glance, you will transfer no energy. So on the average, for every collision, you will transfer half the energy. So every time a neutron collides with another neutron or with a proton, it will lose half of the energy. So in a few collisions, you will actually reduce its energy from over here down to down here. Okay? Now, there's also a lot of mess here in the middle of the diagrams, which I won't say too much about. This has to do with particular so-called neutron resonances in nuclei that are places where there's a particularly high probability for absorbing the neutron. And if you want to have a well-controlled reaction, of course, you would like to stay away from this energy range, because then there, things are discontinuous. So some energies you absorb a lot, and the next one you don't absorb so much, and so forth. Okay? So designers of reactors learned early on that you actually have to reduce the neutron energy so much that you come into this rather stable regime. Okay? But the difference between the properties of the nuclei 235 and 238 are reflected in these neutron capture probabilities and in the fission probabilities. And it turns out that uranium-235 has a very high fission probability, and uranium-235 actually doesn't have one, and that is why you have to, when you dig uranium out of the ground, it turns out that the dominant fraction of uranium in natural uranium is 238. And therefore, you have to enrich your uranium with 235 in order to have the high fission probabilities. So this is what I show here. So on Earth, natural uranium ore is a mixture of 235 and 238. And 238 is 99.28%, and 235 is only 0.72%. So if you took uranium as you get it out of a mine, there are certain places on the Earth where there are high concentration of uranium. There are uranium ores in the mine, and you have miners that excavate the uranium. So then the natural uranium, you can see here that the fission probability is very low, and essentially is identical to the neutron capture probability. The two curves that we had before lie on top of each other. So that would mean that you will not get any fission out of taking the natural mixture of uranium. On the other hand, if you are able to separate uranium-238 from uranium-235, then what you can do is you can collect the uranium-235 and gradually increase the concentration of your uranium mixture. And here is an example where you have made an enrichment to 4.1% of uranium-235, and then conversely 95.9% of uranium-238. And this is the typical mixture that people use in fission reactors for electricity production. And you can see that with this mixture, the fission probability curve in green here is about a factor of 2 or 3, larger than the neutron capture, and therefore the fission process will occur with a good probability. Okay? So this is why one always talks about enriched uranium, and that is where you have increased the relative concentration of uranium-235. Then one also talks about depleted uranium. Depleted uranium is the uranium that is left after you have taken away some of the uranium-235. Okay? So depleted uranium is natural uranium with a lower concentration of 235. Okay? So to summarize all of the story here, here's a recipe, the nuclear recipe. So if you want to do controlled fission, well, you have to use 235 because it has a high fission probability. You want to slow down the neutrons, so you want to have what is called a moderator, a medium with which neutrons can collide and lose a lot of energy. So that obviously has to be light. If you have a very heavy piece and a neutron comes in, then it will just be reflected. It will keep its energy, it will just bounce back. It's like throwing a rubber ball at the wall. The wall doesn't give in, so the ball will come back with essentially the same energy. But if the wall recoils, then of course the ball that you threw, of course, will lose energy. Okay? So you want to use something light, and that is, for example, heavy water, and that is the reason for why heavy water has been a product that, for example, under the Second World War, and which led up to the Manhattan Project in Norway, they had plans to fabricate, isolate heavy water, and there was a big focus on the heavy water because it could be used as moderators, okay? And then finally, if I wrote the word here controlled, because you don't want, normally, you don't want the process to run away. So how do you control it? Well, you do it by removing, suppose you have three neutrons that come out for every fission. In reality, it's 2.4 on the average, but let's say 3 for simplicity. Then, on average, you want to remove 2 of the 3. So that one reaction starts a new reaction. In that sense, you could have a stable operation, okay? So you want to have something that you can use to remove neutrons from the reactor. And there are certain atomic nuclei that have a very high, particularly high capture cross-section, a very high capture probability for neutrons. And these are materials like boron or cadmium. So these are really the 3 ingredients that you need in order to make a fission process. And this is also what essentially the refinement or the separation of uranium-235 and 238 was really what the Manhattan Project was about under the Second World War. So there was uranium separation. And what I have shown here is some of the pictures of the so-called calutrons that were, it was a big factory, a secret factory that was established in the hills of Tennessee at a plant that was called, given the code name Y12. And what was built there was, essentially, this is a big hole, and it's much longer than this. I've been there once, and it's very impressive because it's a mile long. And inside this hole, you had separators for uranium-235 and 238. And the principle is the one we saw in the beginning when we were discussing how to measure the masses of different isotopes. So essentially, you have a beam of mixed uranium isotopes, so the natural uranium. You send it through a magnet, and the heaviest one, the uranium-238, is going to take a little slightly bigger bend than the uranium-235. And if the magnetic field is strong enough and the instrument is large enough, you actually separate the uranium-235 from the 238, and then operators can go in and scrape off the uranium-235 in one collector and 238 in the other collector. And here's a picture of what was called the Calutron Girls at Oak Ridge in 1943. So behind this, there was a whole alley where you had control panels, and you had these girls here during World War II that were operating the dials. They had no idea what was actually happening behind the wall, but they had just an instruction manual, and you had to keep the meters on a particular setting so that the currents here and the magnetic fields were stable. So this was then led to the separation of the non-fissile 238 from the fissile 235. So a fission reactor, like the ones that are used in many places in the world, is a device that is roughly like this one, and they essentially all have, we follow the same scheme. There are different variants and so forth, but it's the basic concept is really the one I show here. So the reactor itself is a vessel that contains uranium fuel elements that are typically organized in long rods. And when you start with it, you have rods of a very stable metal, for example, like zirconium. And inside, you then stack small pills of enriched uranium. And when you assemble them, the radioactivity is nothing important, because it is basically the radioactivity that corresponds to the uranium-235 and 238 that have half-lives of the order of the billion years. I mean, so the activity is not very high. So you can basically handle it with your fingers. Probably would be well advised to have a mask and some gloves, but basically it's not very lethal, okay? And then if you have the uranium in sufficient density, then you may want either the neutrons that come from the spontaneous fission or from a little radioactive source that can produce neutrons will start the chain reaction. And then the fission fragments will come out from the fuel rods, and then they come up with high velocity, and they will then use their energy inside the reactor core here and transfer their energy to a liquid of some sort. It could be water, it could be molten sodium, which is a salt, and it all depends on how you want to build your reactor, and some things have some constructions have some advantages over other. But basically what happens is that the fission fragments transfer their energy to a liquid. The liquid is taken out and is transfer its heat via a secondary container which contains water, so that the water begins to boil. Then the steam that comes out of the boiling process is taken out, and they can generate a steam turbine and produce electricity. Okay? At the same time, of course, the whole installation here is enclosed in a vessel that should be shock-proof and should also be able to contain any leakage of radioactive materials that could happen as a consequence of an accident or a malfunction or a terrorist attack or whatever. So, of course, that is the idealized design. And then here, after the energy of the steam has been taken out, the water is circled back. And in principle, you can have several loops here of heat exchangers. So you decouple the primary part of the reactor, which contains radioactivity, from the secondary circuits, which are not in any direct contact with what happened inside the core, and therefore are not radioactive. Okay, so there's this decoupling. And then if you want to control the speed at which the reaction occurs, then you have these control rods that can absorb neutrons, and if you plunge them deep down in between the fuel rods, they will capture the neutrons, and then the process dies out. If you pull out the rods, then you will have more neutrons available, and they can start a new fission, and you, in a sense, you increase the flux of the reactor. So this is the basic idea. So you have this so-called primary loop, and then you have the secondary loops, which are completely conventional. You could, for this part here, you could heat it with coal or whatever and produce electricity like we also do. Now, we have spoken about the radioactive waste, and I think it's a good idea to actually look a little bit at what comes out of the fission. And this is a plot that plots the amount of radioactivity coming out of what is called high-level waste. So essentially it's the used fuel rods from a reactor. So here is the activity, and this is plotted in billions of becquerel. A becquerel is a unit that says that you have 1 decay of a radioactive element per second. So a becquerel is just a unit that says 1 decay per second. So above here you have 1,000,000 decays per second. Okay? And then here is, in black, is a plot of how the radioactivity will diminish as a function of time. That is, as a function of number of years after the fuel has been taken out of the reactor. So down here we have 10 years, here we have 1,000 years, and here we have 1,000,000 years, okay? So you can see that the black curve is the sum of all the fission products is declined, and essentially has decreased by 3 orders of magnitude, or a factor of 1,000 or so in 1,000 years. But it continues to decrease up to 1,000,000,000 years, and of course, in a sense, it always continues to be there. But what is the figure of merit? I mean, there will always be radioactivity. There's also radioactivity everywhere in the world, in all the materials that we have. There's trace elements of radioactive material. So what is the figure of merit? Well, the figure of merit must, of course, be to compare to what is the radioactivity of the uranium ore that we dug out of the mountain. Because that, in a sense, is the natural concentration of uranium, for example, in certain mines and mountainous areas, okay? And this is this line here. So this is the radioactivity of the original ore. So in many ways, we can say that the black curve goes down and comes very close to the original ore after 1,000 years. So after 1,000 years, the radioactivity of the fission fragments is at the level of the material that you dug out of the mountain to begin with, and therefore that is the time scale. Now you can also see that after 100 years, now this is a logarithmic scale, so it's a very compressed scale. So after 100 years, the activity is basically up here, so it is very high. And so this is the reason for the intense debate about what to do with the fission fragments, because they are gone typically after 1,000 years, and when you read in the press that they will still be there after millions of years, then it's really an exaggeration, because in fact the activity will be less than it was in the original material. But they will certainly be there up to 1,000 years, and they are significantly there up to 100 years, okay? When we talk about radioactivity, I think it's also probably good to actually look at what are the radiation units that are being thrown around, and what are typical doses, and what do they actually mean? And I've tried to collect a few things. So the unit for a radioactive dose is called a sievert, and it is an energy equivalent. So essentially a sievert is if you transfer energy corresponding to 1 joule to a kilogram. A joule is basically the energy that you liberate if you have 100 grams and you drop it from 1 meter to the floor. Then when the 100 grams hit the floor, then it will transfer, it will create heat corresponding to 1 joule. Okay, so this is a unit that we know about in the normal world. Now, what does this sievert mean in terms of biological equivalence? Well, doctors have found out that a dose of about or up to a quarter of a sievert on 1 day apparently has no discernible effect. Okay? On the other hand, a dose of 10 sievert in 1 day is about a deadly doses. Okay? So that sets the scale of things. Now, we have to relate to the 10 sieverts, which are terminal doses, and therefore there have also been limits set both for the general population and for people who work in the nuclear industry. Okay, and for the general population, the typical limit in Denmark is 5 millisieverts per year. Okay, so that's to compare with 10 sieverts, so that's 2,000 times less. And that is considered to be an absolutely safe limit. For workers in the nuclear industry, there is a limit that is 4 times higher. Now, we also get radiation, of course. We're exposed to radiation in many different contexts. So when we go to the dentist, get an X-ray of a tooth, then we typically get a factor of 1,000 less. We get 5 microsieverts for every X-ray. If we have a mammography, it's about the same level. If you have a big scanning of the chest, then the doses can be 4 or 5 times higher. Okay. There's also, we are constantly exposed to a background of radioactive materials. For example, some of the uranium that is dug out is there, and here is the natural background radiation. So it's about a quarter of a microsievert per hour, and then you have to multiply by a year. Here's a number from the United States. They have much more rock, and therefore the number is higher because there's a high concentration of heavy elements. And then you're up to about 6.2 or 6 millisievert per year. Okay. Now we also have inside ourselves we have radioactive elements, and so we produce a dose of radioactivity which is of the order of 0.4 millisievert. And we actually, if we sleep together or next to somebody for 8 hours, continue every night, well, you actually get a dose of 0.2 millisievert per year just from your partner. So think about that. So increase the distance. If you take a transatlantic flight, you get 9 millisieverts. And if you smoke 30 cigarettes a day, you actually get, you get about 5 times a trip to the United States in an airplane. Okay? So it's not insignificant. Now, we've all been confronted with a terrible accident in Fukushima in Japan. And here I have listed the numbers I've been able to find for the situation as it is now, that in the vicinity of Fukushima now, the dose is of the order of 14 millisievert per hour, so that's very close to the plant. If you go to Tokyo, on the other hand, well, and this you have to compare, of course, to the limits for the general population. So this is, of course, is considerably larger. It's 300 times larger or so than what one would tolerate for the general population. If you move to Tokyo, which is about 200 kilometers away, then here are the doses, and per year they are 0.5 millisievert, so actually a factor of 10 lower than the general level, or acceptable level for the population.
But this is not true. There's many reports from Tokyo of people who've gone out with their own Geiger counters and their own equipment. And they found hotspots in Tokyo that well over what the Geiger counter can measure, which is 9.99 microsieverts per hour. So when you say that Tokyo is 0.062 microsieverts per hour,
these are
I need to know where you found those figures.
Well, I mean, the reported average numbers and from the Atomic Energy Commission are these ones. Now, of course, there are many reports from individual locations, and there are, of course, places where you can have a higher concentration due to wind or other things. But these are the official numbers that I've been able to find.
This is an average for the entire area.
This is the average for Tokyo. Right? They measure in different places, and if they measure it correctly, and if the reports are truthful, of course, then these are the numbers.
Yeah,
okay? You don't believe it, I can hear. Okay? Inside Fukushima, directly inside the plant, there is a problem that you could not send workers in to fix, I mean, the problem with Fukushima, as I was explaining to some people before we were talking about it, was that the plant was in a sense, was very well built. And the Japanese have paid an enormous care in trying to build the facility in such a way that it would not be affected by earthquakes. They have a high protection wall that should be able to take care of tsunamis. So they knew all these things. Now, and in fact, when the accident occurred, or the earthquake occurred and the tsunami occurred, the plant didn't crack and the wall didn't collapse. But water came over the wall, and so what the problem really was that the cooling facilities that had been installed around the plant, they had actually been put down. They excavated big holes, concrete holes, and they put the pumps that were supposed to supply, for example, the cooling water and the generators for electricity that were supposed to start up if there was an electricity failure. They were put down in the lowest place. So when some of the water came over the wall, of course it went down into these holes, short-circuited the pumps and the generators, and then the plant was shut down, and all the security features were shut down. So in many ways, the designers had thought about taking care of the threat of earthquake and tsunami, but they made some, in hindsight, absolutely trivial mistakes for no obvious reason. If they had just raised the generators and the pumps up on a platform, in all likelihood, nothing would have happened in Japan. Okay, so this is a lesson, of course, to take home. Yeah?
I'm sorry, it's just because you say that it was only, I'm sorry, but it's because you say that, no, because afterwards, it's a very important thing, because at the moment, you've got in Fukushima, your figures that you've got now, they say, oh, there's no problem, everything's fine, but there's hundreds of reports from there where people have gone out and got their own equipment. There's doctors in a city, I forget the name now, 200 kilometers from Fukushima, and they tested a few hundred of their equipment.
I've no, yeah.
Cesium in their urine, and this is 200 kilometers away. And you say you're being here very blasé, explaining a lot of the technicalities. I'm not meaning to be rude, but it's
I think actually you are being very rude. Questions and comments are supposed to be.
It's absolutely okay. I mean, I'm not. Yeah, I'm not. I have no issue actually. Arguing with the official reports. I mean, what I'm trying to do here this evening is explain, in a sense, the basics of it, and I've tried to collect figures that are publicly available. And these are the official figures. Now, if people are worried that these figures are not correct, fine. I mean, I have no issue with that. Right? But these are things we can all look up on the web, and then we can, of course, discuss whether the sources are correct or not. I myself have no particular, knowing Japanese physicists, I have no particular concern about the correctness of the figures. So I think that is basically all right. Now, what we should be concerned about is why could such an incident happen in the first place? And that is really what I'm concerned, okay? Okay. Now, I explained a little bit about the conventional fission reactor, and I showed a picture. Now, we also all read in the press that there are other types of reactors that are being considered, and there are things that are called breeder reactors. And let me just say a few words about what that is, so that you can understand or have a sense of what it is when you read in the newspapers. Now, the point is that in the conventional reactor, with the scheme that I showed before, then which is called also a once-through reactor, you have some radioactive fuel, enriched uranium, you put it in the reactor, it operates for a certain amount of time, you take the fuel out, okay? Then you have basically only used 1% of the available energy. So there's a way of increasing the energy efficiency, which actually also can have some very beneficial consequences. And the idea is basically that in the reactor you could produce, because, well, I should interject, that if we look at a prognosis for the world, people also agree that it will be very expensive getting enough uranium, and there's a shortage of uranium. So it's not clear that if one wanted, I'm not saying that one wants to, but if one wanted to base the world's energy production on uranium, there we would also run into shortage problems. And so therefore you are not satisfied with a situation where you only use 1% of the available energy, okay? So if you can make a reactor where you produce new fissile material, then of course you would increase your efficiency dramatically. And you can do that because if in the reactor you, for example, have plutonium, I'll come back to plutonium in a moment, you have a reactor with plutonium, then you put uranium-238 around, and then if you can do neutron capture. So uranium-238 can capture a neutron, make neptunium, and neptunium can end up producing plutonium. And that's the same fuel that you want to use in your reactor again. So in a sense, you could come, if you had a stable operation and a stable situation, you can actually produce new fuel of the same kind inside the reactor. And that is called a breeder reactor, and they come in different varieties. And they have been discussed a lot, but of course there are some good sides about it, but there are also some negative sides. There are also new ideas around where one, well, in Fukushima, the very great concern, of course, was a meltdown. Now, the amount of fissile material is not enough, and the density is not enough to make an explosion in the form of a bomb. But if the cooling systems and the neutron capture systems that should regulate the process inside the reactor, they don't function, then the temperature inside the reactor can increase dramatically. And we could come into a situation where there is what is called a meltdown, namely that the material sort of burns its way through the enclosures of the plant and then evaporate into the air, and the fission fragments and all the radioactive material then is liberated into the air and deposited in the surroundings. So this is, in many ways, the worst case scenario of the nuclear reactors, and we have seen, well, we saw Chernobyl, and we have also seen what happened in Fukushima, where there's a partial meltdown. So it was an extremely serious situation, and it could have gone much worse. And in Japan, one was actually lucky that the damages were rather contained. But now, is there a way of avoiding this? Well, of course, the way of avoiding it is having a reaction that by principle cannot run away. And so one idea that is being explored is actually coupling a reactor with an accelerator system. So if you have an accelerator that runs on electricity, then you can accelerate protons, and the protons can be shot onto nuclei, and then they will transfer energy to the nuclei, and there is a process called spallation, where out of it you get more protons and neutrons. And these neutrons could then go and irradiate the uranium fuel and create the fission. Now, if you have a problem then, what you do is you turn off the power to the accelerator, and then you don't have a self-sustainable chain reaction. So the reactor is not critical, it operates in what we call a subcritical mode, okay? So these are some of the things that are being explored. And this is a completely new design, and in fact, there's in Belgium, they are trying to couple an existing research reactor to an accelerator, and it will explore the scheme. So this might be a way out of the present situation for the future of having these so-called accelerator-driven systems. Now, coupling reactors to accelerators could also have another very beneficial application, namely that of waste transmutation. The radioactivity, as we saw before, well, I mean, there are kind of two kinds. So, for example, plutonium, uranium, and the heavier elements that can be created out of uranium, like plutonium, they are typically long-lived. They have very long lifetimes of tens of thousands of years or hundreds of thousands of years. On the other hand, many of the radioactive fission fragments, but then also the strontium-90 that I talked about, are rather short-lived. But suppose you could take the long-lived, which are really the main concern. If you have to store something for 30 years, well, it could be a problem, or 100 years can also be a problem, but it is manageable. I mean, the very big concern is that you have to deposit something for 1,000 years, because many generations beyond our own. But if you could now shoot protons onto these heavy, long-lived radioactive elements that are in the waste, then you could actually break them apart, and then you would transform them, for example, to short-lived isotopes. So in a sense, there are possibilities now, and this is a very active research topic, where one actually tries to optimize the processes around waste transmutation, and one could actually, there's a way out of all the junk that has been accumulated over the last 50 years, in principle. It's not going to be cheap, but in principle, there's a way out, okay? Now, another of the big concerns, of course, is what we call proliferation. That is that nuclear material that in principle is fissile can be stolen or be sold or be used to fabricate weapons. And here I have listed what is required. Now, we saw before that in a reactor, the concentration of uranium-235 is typically 4.1%. That's the mixture. For a weapon, you do something else. You have a almost pure, the pure metal of uranium, either typically 235 or plutonium-239. And here I've indicated what is the critical mass. And basically, the little cartoon here indicates that if you have too little mass, then some of the neutrons that have to start a new reaction and entertain or keep the chain reaction flowing, they will escape. If you have sufficient quantity, then only few neutrons escape, and they will have time to react in between. So there is a critical size, and this is what is called the critical size of for the bomb, the critical mass for the bomb. You can then, if you want to enhance this, you can put a reflector, a neutron reflector around that will bounce some of these neutrons back, and that will then increase the efficiency. So bomb makers have been playing all these games here and trying to optimize these processes. So what I have listed here is that for a sustained chain reaction for a weapon production, then uranium-235 you need about 56 kilograms, okay? And if you look up the density of uranium-235, it corresponds to a sphere of about 17 centimeters in diameter, so it's smaller than a bowling ball, okay? For plutonium-239, which is the preferred fission weapon, the critical mass is actually down to 10 kilograms. And that is a sphere of less than 10 centimeters in diameter. And of course, there lies the very big concern about proliferation, because it doesn't actually take very much plutonium to make a bomb. So the plutonium is produced in the reactors, and I've listed here the reactions. So if you have the 238 we were talking about that is not very good as a fissile material, if it's bombarded with a neutron and absorbs this neutron, it can make Neptunium-239 that decays to 239 plutonium, which then is the one that with 10 kilograms you can actually make a bomb, okay? So the nuclear waste that comes out, particularly from plants in politically sensitive regions of the world, is a very big concern because it gives the possibility for creating what has been called dirty bombs. And here are just two examples of a plutonium bomb and a uranium bomb, the way they were used in World War II. So typically what people do is they have to keep the fissile material into two pieces that are separate, and then when you want a detonation, you bring the two together. And for the uranium bomb, typically this was done like a gun. That is a conventional explosive that shoots a piece, the missing piece of uranium-235 onto another piece of uranium-235. If it happens fast enough, you suddenly have this critical mass, and the chain reaction will proceed completely uncontrolled. For plutonium, there are other variants where one uses conventional explosives that sort of compress the plutonium, and then one can make a bomb with about these materials. So it's clear that terrorists typically will probably have a difficulty in creating the most effective weapon because there are rather complicated details in making this work. But of course, the concern is that it doesn't have to be a bomb with the full explosive power that is made, and there could be quite a significant direct damage and collateral damage coming from the release of radioactive material. So proliferation is certainly a very serious concern in the world. Okay, I will just use the last few moments explaining what happens in the fusion process. Now I've been speaking about fission on one end of the scale. In the other end of the scale, we can also win energy by fusion. And this is the way we have made heavy elements in the early universe. So essentially, you fuse neutrons and protons, and they fuse together and make deuterons. If two deuterons meet again, they can make one of the most stable elements that ultimately is helium-4. And all of this happened in a very short time window after the Big Bang, 3 minutes after the Big Bang. We know we can calculate this very precisely. So up here you have the number of neutrons, and then what happened is in a very short time window, essentially what you had to do is you had to form these deuterium nuclei, one proton and one nuclei. You had to form them very quickly in the beginning. But in the early universe, when it was very compact, there were many gamma rays. They could instantly break up a deuterium nucleus again. So you had to wait for a certain amount of time until the gamma rays that were zapping around the universe had decreased in numbers. And that typically happened after 3 minutes. And then you could form deuterium, which is, let's see here, is the green curve. So all your neutrons and protons are eaten up, they form deuterium. And then immediately afterwards, you form helium-4, which is the gray line up here. And then if essentially all the neutrons and protons are used, and those neutrons that are left over, they will disappear because a neutron has a half-life of 15 minutes. So they will not be present in the universe much longer. So therefore, we actually know that these processes in the early universe happened this time window, which is fantastically precise, from 3 minutes to about 15 minutes. So it's one of the big, fantastic discoveries of the 20th century, our understanding. So in the stars, the energy that we receive is produced by fusion, and it's basically the same process. So you have a whole chain of reactions that start with protons and that ultimately lead to helium-4. And there's a release of energy that is about 10 times lower than the energy that is released in a fission process. Now, all of these processes happen in a controlled way in the sun because, again, it is a quantum mechanical reaction process, namely that the fusion here, you have to collide things that are positively charged. And so the probability for the reaction is illustrated here. You're actually not above the so-called barrier. So this is, in a sense, a parallel to the fission process. If to fuse, you have to come over this barrier. But in the sun, the temperature in the interior of the sun is not sufficient to be over the barrier. So therefore, the processes that actually occur because there is a probability of actually doing the reaction, even though it is in principle forbidden. Otherwise, the sun would have burned away a long time ago. So a star like ours only functions and is stable, has a lifetime. It's been around for about 5 billion years. It will probably be around for another 5 billion years. So this lifetime is only there because of the barrier penetration probability. Okay, so the idea of the fusion reaction or the fusion reactor is a different one. Start with, for example, heavy hydrogen, deuterium, or tritium, a proton with 2 neutrons, and make fusion. But this requires, of course, high temperatures, because you don't want just to be running with a low reaction probability. The sun can do that because the sun is so large. If you want to apply it under terrestrial condition, then you want to increase the energy, you want to increase the temperature. And there's a design for a machine that can do that. It's called the tokamak. Essentially, it is a donut where you keep a plasma of the nuclei and electrons running around in the middle, and in this plasma here that the reactions occur. And then you take out the energy, again in the form of heat, and then you can drive a turbine, an electricity generator. And here's a picture of an experimental facility. There was the jet in England, and there's a new facility which is being built with the cooperation of all the European countries and many others in the south of France. It's called ITER, that will try to produce energy by this way, by fusion instead of fission. Okay, so I have listed a few pluses and a few minuses. So fusion is the same process in the stars, so it's well understood. It relies on deuterium. So plenty of fuel. There's no chain reaction possible. There's no radioactive fission fragments. All of this is very attractive. Of course, nothing is perfect. There will be neutrons, and you can activate the machine components, so there will still be some radioactivity, but typically not a serious one. The production stability hasn't been demonstrated yet, and from all the present knowledge, it seems that large-scale electricity production will require some gigantic installations, so that one country cannot build, for example, Denmark. It would probably be inconceivable that Denmark could have its own fusion reactor, and there, of course, so that creates other considerations in terms of supply stability in a changing world. Okay, so this brings me to the end, some of the perspectives on this topic. So nuclear power today comes from about 435 fission reactors. France is the country that produces most electricity by fissions, about 78%. Belgium is number 2 with about 54%. Belarus with 54%. Sweden, next door, actually produces 40% of its electricity by the nuclear. Japan is around 18%. The United States, 19%. And China, so far, only 1.8%. But China has expressed that they want to increase this to about 30% in the coming years. Now, the basic processes I've tried to describe are well understood. I think it's also worth to say that objectively, in spite of the accidents that we have witnessed, the accidents and deaths from nuclear industry are rarer or significantly rarer than as a consequence of large-scale exploitation, mining, and burning of fossil fuels. So this is well documented. However, of course, it is very difficult to handle a situation like the one in Japan, where one had risked actually to contaminate Tokyo, a city with over 10 million inhabitants. So the main challenges are the storage of the radioactive waste, and I would say the security in connection with technical and human errors. natural disasters, and of course terrorism. Now in the future there may be, as I've explained, there may be reactors that will be driven by an accelerator. They have the advantage that you can turn off the key and then no chain reaction will be possible. We also have to remember that we are 7 billion people on Earth today. In the UN's projection are that in 2050 we are going to be perhaps around 9 billion people, perhaps 10 or 11 by 2100. There's no doubt that the curve will flatten out. But of course, all these people will have a legitimate desire to acquire a standard of living like the one, for example, we enjoy. And therefore, the electricity demands in the coming years is going to be enormous. And somehow we are going to have to adjust to supplying that on a stable basis. Fusion reactors, which I mentioned at the end, are still in the research and development phase. It's very unlikely that they will be able to supply any alternative before the next 30 to 50 years. And finally, which is much to be preferred, sustainable energy like the sun and wind is really a major opportunity. It's of course also a major challenge. The way things are going today, I would say that it requires a massive political support with which one doesn't really see. So it is hard to see that the sustainable energy will, on a competitive level, be able to compete over this time scale either. So I think that sets the scale for the nuclear energy discussion again. Okay, thanks very much. I think I end here. Thanks for your attention.
Yeah, thank you for an informative talk. So we have time for a couple of questions.
What is cold fusion exactly? Or I've heard of that. What's that?
Yeah, cold fusion was something that came up as a potential new energy source. That was the hope, and I guess it was, when was it? In the early 90s, I guess. So it was a group of researchers in the United States who thought that they had observed that by compressing deuterium. Now, in the fusion process, you want to fuse two deuterium nuclei and then eventually produce helium-4. There's an energy release. But it's actually very difficult because the deuterium nuclei repel each other, and therefore you have to supply energy to get them close enough so they can fuse. Now, they claimed that they had discovered a process by which you could trap deuterium gas in various metals, and that suddenly this facilitated the fusion reaction. And they call this the cold fusion. Of course, it would violate energy conservation as we know it, and therefore people were immediately skeptical. On the other hand, the potential implications that there was a new phenomenon at stake was so colossal that the media went bananas, and many people also did it. I remember at the particular time I was actually in Dallas for a physics meeting, and there was a meeting of the American Chemical Society, and they had rented a whole stadium. There was, I think there was about 5,000 to 10,000 people there, and it was completely impossible to actually ask a question because the whole floor and those that were allowed to ask questions, they came from the military and they came from the oil companies and so forth. So people really, in that period, the first 2 weeks, wanted to believe it so much because it would have proven, an inexhaustible energy resource. You could produce energy on your tabletop. Of course, there were some clear mistakes. I remember it was flashed the spectrum of one of these neutrons, and anybody who had ever measured neutrons could see that they had the amplifier was not functioning the right way. So it took a few weeks or a month, and then of course the whole story died out. But so that was the story of cold fusion. So it was propelled by the enormous hope, of course, that we could find a new energy, cheap and simple energy source for mankind. But it was a fluke.
Do you have any update on how the ITER project is going? I mean, have they managed to make this self-sustained?
No, it's far from that. It's just it was decided a few years ago, and the facility is being built. So there will be, I don't know exactly how how long it will take until they can go into the first stages, but at least my guess is at least 10 years before it even becomes partly operational. So these are very complicated facilities, very expensive, and it will take a very long time. And before you then get a result and you can evaluate it, and then you would have to go to a facility that could actually produce energy. In the beginning, you will have no significant net energy gain.
But just an inside question, I mean, how good would the energy production be? I mean, if you compare with a liter of gasoline and you have a liter of the deuterium, how good is the energy production compared to that? If it's supposed to be,
that's always a question of the price. If the price of gas continues to increase, of course, there are other technologies that suddenly will become competitive. I mean, solar panels, for example, the cost of electricity is not terribly today over the cost of producing electricity from fossil fuels. Of course, if the industry and societies go that way, I mean, you have to become competitive because the voters typically will not accept to pay more for a product that comes from one source than the other. So it's a question of whether you, on the other hand, what you're used to increases so much, then other technologies become advantageous, or you are able, by mass production, actually to reduce the cost of the newer technologies. And hopefully both things will come into operation. And that is, of course, what will drive the new technologies along.
Okay, I think we're running a bit late, so we'll stop the Q&A here. But Jens-Jørgen will hang around, so you're very welcome to come by and ask him questions. So this is the last session of the season of Science and Cocktails. Thanks a lot for coming. We'll be back in the fall with new inspiring talks. So follow us on Facebook, and feel free to suggest topics that you'd like to hear about. So let's give a last round of applause to Jens-Jørgen for.
Thank you.